You ran your regression, everything looked clean, the p-values were nice, R-square looked good, and then your supervisor says, this is not the right model. That moment feels frustrating, but most of the time, the problem is not your analysis, it's your model choice. In research, regression is not one size fits all. The type of model you choose depends heavily on what your dependent variable actually looks like. And here's the tricky part. Different types of data can look similar at first, but behave completely differently. Let's start with what we all know, continuous data. Things like crop yield, income, soil moisture, temperature. These can take any value, including decimals. For this type, we usually go with linear regression, but there's a hidden assumption, linearity. That means when x increases, y should increase or decrease in a straight line pattern. But in real-world systems, especially in agriculture, that's often not true. Think about fertilizer and yield. Yield increases with fertilizer, but only up to a point. After that, adding more fertilizer doesn't help. It may even reduce yield. This is where linear regression fails because the relationship is not purely linear. In such cases, a much better approach is the linear plateau model. It captures two phases. First, a linear increase, and then a plateau where the response stabilizes. This is extremely useful in soil science, crop response studies, and nutrient management because it reflects biological reality much better than a straight line. Now, let's talk about a situation many people overlook, censored data. Imagine you're studying household savings. Many people report zero savings. But does zero really mean zero? Not always. Some people might actually be in debt, but your data cannot go below zero. So the values are cut off at a limit. That's called censoring. If you apply linear regression here, you'll get biased results. Instead, you should use a Tobit model, which is designed for this kind of limited data. Next comes count data, numbers like 0, 1, 2, 3, no decimals. For example, number of cows, number of visits, number of adoption events. These are not amounts, they are counts. If you apply linear regression here, you might end up predicting negative cows, which obviously makes no sense. So instead, we use Poisson regression. But again, reality complicates things. In many datasets, the variation is much larger than expected. Some farmers never adopt, while others adopt many times. This creates overdispersion when variance is greater than the mean. In that case, Poisson breaks down, and we switch to negative binomial regression. And sometimes the problem gets even worse. Too many zeros. Think about awards, disease cases, or rare events. Most observations are zero. This is called zero inflation. Then we need specialized models like zero-inflated Poisson or zero-inflated negative binomial. Now let's move to categorical outcomes. If your dependent variable is yes or no, like adoption or non-adoption, you use logistic regression. If there are multiple categories, like crop type, you go for multinomial logistic regression. But here's a common mistake, ignoring order. If your categories have a natural ranking, like low, medium, high, then you shouldn't treat them as unrelated groups. You should use ordered logistic regression. Otherwise, you lose important structure in your data. Now comes a completely different category, time to event data. Here, you're not just measuring what happened, you're measuring when it happened. For example, how long it takes for a farmer to adopt a technology, or how long a machine lasts before failure. And here's the catch. Some observations are incomplete. Maybe the study ends before the event happens. This is called censoring in survival analysis, and it's different from Tobit censoring. In these cases, regular regression doesn't work. Instead, we use survival analysis, like the Cox regression model. Finally, there are cases where you don't have just one outcome, but several related ones. For example, a farmer may adopt improved seeds, fertilizer, irrigation, and pesticides. Each is a yes or no decision, but they are not independent. If someone adopts one technology, they are more likely to adopt others. To handle this kind of correlation, we use multivariate probit models. So the takeaway is simple but powerful. Good analysis is not about running regression. It's about understanding your data first and then choosing the right model. Because even a perfect model applied to the wrong data gives you the wrong story.